Hi everyone, I'm Thorn and I'm currently a student at the University of Eindhoven. I'll be presenting the paper Does the duration of rapid release cycles affect the bug handling activity? This research has been conducted in collaboration with Eleni Constantinou from the TU Eindhoven and Zainab Abul Khalil and Tom Mansk from the University of Mons in Belgium. Software development often follows a cyclic pattern, so-called release cycles. To maintain user satisfaction in software projects, consecutive software releases need to introduce new functionalities and fix issues that negatively affect user experience. Bugs in particular have a negative impact on user experience, as they prevent the user to work smoothly with the released software product. Different projects run release cycles of different lengths to address the bugs and add functionality in the most optimal way. There are two main ways in which release cycle length is determined for a software project: feature-based and time-based. As the name suggests, in feature-based, releases occur when planned feature of the software is ready, whereas in time-based, every X time units, for example every 4 weeks, a release takes place. Both approaches have their own advantages. The main benefit of feature-based is that once a feature is ready, the user will receive it. The main benefit of time-based is that users and external dependents on the project can plan ahead, as they know exactly when the next release will become available. Recently, it can be observed that projects tend to switch to shorter release cycles with as goal to provide new functionality and fixes faster. Two examples of projects which have made this change are Mozilla Firefox and Eclipse, where both Firefox and Eclipse moved from annual to quarterly releases. There exists quite some research on the effects of switching from longer release cycles to more rapid releases. The slides show some examples of publications on the matter. However, to the best of our knowledge, there is no research on the effect of varying rapid release cycle durations on the bug handling activity, providing us with an opportunity to investigate this specific case. But why specifically bug handling? As mentioned before, to retain user satisfaction, projects need to resolve problems negatively impacting user experience. Bugs in the software contribute to negative user experience. It is at worst annoying if a functionality is missing and it can potentially turn away new users, but having software not perform up to the specifications, able to do the advertised tasks, can lead to existing users to stop using the software, or it may prevent new users from starting to use it. Therefore, we want to find ways to prevent bugs and investigate what effects of different rapid release cycles there are on the bug handling activity. Specifically, we want to understand which aspects of the release cycle affect bug handling and how. We would like to know if there exist release strategies that are more efficient in handling bugs and keeping users satisfied, without imposing too much burden on the developers that need to handle the bugs. This leads us to the two main research goals: study the impact of rapid release cycle durations on the bug handling process, and study whether variations in the rapid release cycle duration affects the bug handling process. To study these research goals, we chose the research method of quantitative empirical evaluation based on the historic open source software project data. To perform this empirical evaluation, we need a dataset. Before collecting this, it's important to define what we consider a rapid release cycle. We consider a project to have a rapid release cycle when the average release cycle duration is between 5 and 35 days. This duration is based on the rapid release dataset created by Joshi, who defines rapid release cycles as releases with a duration of on average being between 5 and 35 days. This dataset contains 994 projects, repositories meeting our definition of rapid release projects. Joshi mentions which repositories to focus on, but does not provide all information required for our investigation. Therefore, we had to enhance the dataset by mining GitHub. Specifically, we have mined the considered projects to obtain metadata about their releases, issues, and issue events. Where issues contain the information directly relevant to the issue, its text, who created it, when it was created, etc., and issue events track the time and occurrences of interactions with an issue. Think of if and when people were assigned to the issue, if and when commits were referenced, etc. We investigate GitHub issues as issues are used as the bug tracker of GitHub. However, in almost all considered projects, GitHub issues are not solely used for bugs. They are also used for posting feature requests or questions asked by user to the development team, and many more uses. GitHub does not provide any predefined way to distinguish those different types of issues. Therefore, we needed to provide a way to detect which issues actually correspond to bug reports. To do so, we relied on the use of GitHub issue labels. GitHub contributors can assign 0, 1, or more labels to the posted issues. Examples of such labels are shown on the slide. Think of bug, enhancement, question, documentation, duplicates, help wanted, etc. etc. Due to their descriptive nature, we can use these labels to classify which issues actually represent bugs. Based on an inter-rater agreement process, we manually classified the labels in the 994 repos to come to an acceptable classification of the labels corresponding to bugs. Unfortunately, not all 994 projects from the rapid release dataset could be used in our investigation. For example, we needed to exclude projects with not enough releases, too little issues, or having no labels on their issues. To do so, we filtered the repositories based on minimum thresholds on the number of releases, number of issues, and the label coverage. Since we use labels to classify issues, we can only consider issues which have at least one label attached. However, this leaves projects with very few issues labeled. As we investigate on a per project basis, we need to discard the projects with too few labeled issues, such that they do not bias the results. We only take the projects with at least 40% of their issues labeled. This gives the statistics which are presented on the table on the slide. As you can see, this still leaves a very significant number of issues. The third filtering condition was the number of releases, of which we have a minimum of 15. The distribution of the releases can be observed in the box and plot on the slide. Statistics of the releases can be observed in the table. As you can see, the minimum amount of releases we have in the projects we use is 15, and we consider this a significant number of releases. Now that we have seen the data set for our research, let's look at the research questions. The first RQ we investigate in our research is investigating how the bug fixing process is affected by the rapid release cycle duration. This is followed by RQ2 investigating the survival of bugs over multiple releases. RQ3 investigates how the bug triaging process is affected by the rapid release cycle duration. Lastly, we have RQ4, which investigates whether and how variations in the rapid release cycle affects the bug handling process. There are a couple of relevant metrics for answering our research questions. First, let us understand the concept of fixing time and triaging time. The fixing time is from the opening of the bug till the closing time of the bug, but there must be a commit referenced in between. The triaging time is the duration from the opening from the bug until there is a developer assigned to the issue. The bug does not need to be closed for it to be assigned or have a triaging time, and the bug can be fixed without having somebody assigned. These two definitions are used in the metrics of triaging ratio, triaging duration, bug fixing ratio, and bug fixing duration. The third and last metric aims to measure bug survival. A bug is surviving when it's opened and there is, in for example, release 1, and there is one or more new releases in between. As you can see on the slide, this means that bug B is surviving, as it's only closed in a few releases after. A bug is not surviving when it's opened and closed in the same release. This concludes the metrics we need to answer our research questions. To answer research question 1, 2, and 3, we use a method proposed by Nayebi et al., the Gandhi-Washington method. GWM is designed to analyze the impact of recurring events, which it clearly is what we've done in our research. GWM consists of 3 stages: encoding, categorization, and the synthesizing stage. In the encoding stage, the data fed to GWM is a list of projects with, for each project, a list of all the subsequent release durations together with the variable of interest, for example, fixing ratio or fixing duration. The release durations are then encoded as a letter to user-specified encoding. The one we have used is visible on the slide. Where releases taking between 2 and 5 days we have encoded as A, releases between 6 and 20 days we have encoded as B, etc., etc. Once this completes, the list of characters with the variable of interest is passed to the categorization stage. In the categorization stage, each of the sequences of characters is transformed into a regular expression. For example, triple A and then 4 times a B is transformed into A star B star, where the star is the clean operation. The most generic regular expression we can have with the encoding shown in the encoding section is A star B star C star D star E star, and this all wrapped by another star, as this would express any combinations of letter possible with these 5 letters. The regular expressions together with the variable of interest is passed to the last stage, the synthesis stage. This stage combines all the variables of interest for each unique regular expression. It then creates a tree of regular expressions with the most specific ones at the bottom and the most generic one at the root. It then pairwise compares the regular expression variables of interest to see if there is a statistical difference. If there is no statistical difference, the regular expressions get merged until only statistically different regular expressions remain. This is then the outcome of the GWM method. Now that we've understood the method to use to analyze the effects of the recurring events, the releases, and we understand the metrics and how we computed these variables of interest, we can look at the results obtained. For RQ1, we investigate bug fixing ratio and bug fixing duration, and if they have significantly different results for the project with a rapid release cycle duration. From the results from the GWM method, we could not find a statistical difference between the two metrics and the release cycle durations. For RQ2, we investigated the bug surviving ratio, again using the Gandhi-Washington method. Also for this RQ, we could not find a statistically significant difference between the bug surviving and the rapid survival and the rapid release cycle durations. The last RQ we investigated using the GWM method is RQ3, focusing on the triaging process, specifically on the triaging duration and the triaging ratio. Also for this RQ, there was no statistically significant difference between the bug triaging and the rapid release cycle durations. The last RQ we investigated focused on the variability of the release cycle durations and their effects on the bug fixing process. For this, we looked at the IQR versus the bug fixing ratio and the bug fixing duration. See the two plots on the slides for the distribution. To measure the correlation, we used the D'Agostino-Pearson normality test. As both scores were close to 0, we did not find any correlation between the variation in the release cycle duration and the bug handling process. We have the results for the 4 research questions we posed guiding our investigation. Clearly, the results are negative results, in the way that they show we could not find a correlation or statistical dependency between the rapid release cycle duration and the bug handling process. This was opposite to our initial expectations, as we expected to see some correlation or dependency, especially as the research looking at traditional release cycles and comparing them to rapid release cycles did find a difference between the two types of release cycles. For now, we can conclude that there is no ideal rapid release cycle duration with respect to bug handling, and the investigated aspects of bug handling do not seem to be affected by the rapid release cycle duration. However, this is still an interesting observation. Do note, we only studied the rapid release cycle duration and its effect on the bug handling process. There are still opportunities to focus on other variables and factors together with rapid release cycle duration and see if they have a significant effect on the bug handling activity, leaving room for future work and extending this research.